Right, I left you last time with a cliffhanger, and so I wanted to rush through that stuff so that you could all sit down at lunch and go, no, really didn't understand the Higgs mechanism. So let's go back and go over that. So think about an electron, which we've been thinking of as just a point particle, and then the mass is just a label on it, just a number we've attached to it, which determines its properties. The idea behind the Higgs mechanism is one of the things it does. It has a number of advantages, but in terms of the parameters, which is really what we're interested in, instead of just this number being attached to the particle, there is now a universal number which is the same for all of these, which is determined by the Higgs field, which is just a field that permeates through all of space. And what it does is it determines the mass of the particles by how strongly they feel that field. So you might want to think of it, I'll use the example of a swamp. Maybe you want to think of it like air resistance. So something very, this Yakoa parameter, if it's very small, then you don't really feel the wind resistance, so you can sort of cut straight through the field. And if it's very large, then you have a large mass. Okay? So let's get back to this diagram. The whole point of this was, this is one of the parameters in what's called the potential for the Higgs field. So this number we don't know, it's a fundamental parameter, which means, if you want to know what it is, go out and measure it. So we could think of changing this number. And what we did last time was we started with our domain here, and we just started going slightly to the right. And what that did was, it made sorry, I've got a lozenge, I'm just finishing. We're okay. The pack comes with little koalas on it, so I'm feeling quite good about that. It made the range of the strong force longer, so those muscly arms could reach out further, which meant that, as well as deuterium, which is bound in our universe, we also have the diproton bound. So if you take two protons, if you can overcome their electrostatic repulsion from each other, if you get hot enough, close enough so that those muscly arms can reach out and grab each other, they will hold on, it will be stable for a significant period of time. Okay? Now the problem that could raise was it gives the early universe a shortcut to make helium. And that's bad because we need hydrogen both to form H2O, water, and a large number of other chemical compounds. And we need stars to run on hydrogen because it's the best fuel. It's the fuel that has the most energy inside it. Now, what I went on to say, that's where I left you with the cliffhanger. So what actually happens is a bit different. So the papers I'm referring you to now are these two, which are too low to see, if you want to look them up. There is a window of opportunity in the early universe. Okay, the early universe is very, very hot. So if you want to make the diproton, if it's too early, then there's too much energy in the photons, and if a photon hits that, it will disintegrate. It'll make it fall apart. So it's too early. You just got to wait a bit until things cool off, and then you'll make the diproton. But if you wait too long, there's not enough energy in the two protons for them to overcome the electrostatic repulsion and actually get it within the range of that strong muscly arm. So there's a window. And what these guys actually calculated is just binding the diproton is not enough to open that window. Okay? If you just bind the diproton, actually that window is closed. By the time the photons will let it happen, the protons won't do it. Okay? This is important because this is, we've actually started off with a sort of cautionary tale. This is one of a very common example in some of the literature, and it's actually not quite as disastrous as some people think. There's another region which Robin might tell you more about. Even if you could make the diproton, it's not necessarily true that it would immediately make helium. That reaction might be too slow. In particular, on the way to making helium, you first need to make deuterium. And by the time you make deuterium, it may be too late for any more nuclear reactions. Remember, all those nuclear reactions happen between about 3 and 20 minutes. So even if you make diproton, if from here to here it takes you half an hour, then it's too late for anything interesting to happen. Another potential problem is in stars. There we go. You remember, geez, that's way too low. Okay, let me just tell you about it. The first step in making stars is that you take 2 hydrogen atoms, you smash them together, and you make deuterium. Now, you make two protons, same thing, and make deuterium. Now, you need a weak interaction to kick in at just the right time to turn the proton into a neutron to make that happen. If you can make the diproton, then you shortcut stars. Now, what you sometimes read in the literature is that this would mean that stars would burn a lot faster. But again, that's not true. As I said before, how fast a star burns depends on its macroscopic properties. It has to maintain stability, and that determines the microphysics. The rate at which these particles hit each other, that's the microphysics, but that is determined by the macroscopic stability stability issues. What that means is that, if in the sun right now, I could flick a switch and the diproton would be unstable, then the sun would be in a huge problem, right? The basic reaction would run about 10 to the 18 times faster, okay? So that would be a huge problem, but that's obviously not going to happen in any universe which starts from the beginning with a bound diproton. It's just not going to the star wouldn't get itself in that mess, basically. That said, we're not entirely sure what happens to stars if you make a stable diproton. It might be the case that stars will burn, but to burn slowly, they burn at a very low temperature. Now that's no good, because the temperature of the surface of the sun determines how much energy there is in each photon that comes from the sun, okay? Now, if you want to do something interesting with those photons, like photosynthesis in the leaves of plants, you'll need the energy in each photon to be at about the right level to break molecular bonds, so that you can actually do chemical reactions with photons starting it off, okay? If the temperature of the star is too low, that won't happen. The most that will happen is a bit like what happens in a microwave, where you don't actually break any chemical bonds, you just jiggle everything until it gets hot, which is not really, you can't, you won't be able to break apart carbon dioxide to make oxygen in stars. You won't be able to do any of those important organic reactions. So a stable diproton might not be the sort of disaster that a lot of things show it to be. So that's sort of, we started with a cautionary tale that, a lot of these cases, they're a bit more subtle than we need to think. Okay. Yep.
We can just slide this over, and then you'll be out.
Magic. This is genius.
It's actually Dean's idea.
Yeah, up there for thinking. Hang on, let me just. Yeah, good. Okay, fantastic. That was for a fairly small decrease. We went this way just a bit. If you go a bit further, the next major, these things really happen in stages. So whether or not say the diproton is stable is very much a switch. It is and then it isn't. So you have a very rapid change. The next very rapid change is that instead of neutrons decaying into protons, it goes the other way. So remember I said that neutrons are unstable. If you just have one lying around in your hand, if you wait, I think it's a couple of minutes, I can't remember what it is, it will decay into a proton plus a few extra pieces. You go a bit further to the right, and it's the other way around. Protons decay into neutrons. This is a problem, because that leftover hydrogen from the universe, which is going to go and power stars, that's just that's just leftover protons. So there are two ways that this could go, depending on how the early universe starts cooking things. Either because you've got so many neutrons and you don't have, remember the protons were repelling each other, so they might not. So actually doing nuclear reactions is hard. For two neutrons, there's no repulsion. So you have a universe where nuclear reactions are easy, which is a bad thing, okay? So either you get runaway fusion to make really, really massive nuclei, or else most of the free baryons are just free neutrons. The problem with that then is that you don't particularly need stars to start making nuclear reactions. Diffuse gas will start doing it. It'll keep the gas hot and diffuse, so it's going to affect galaxy formation, because the galaxy formation, remember, the gas has to cool. But if it collapses a bit and then, nuclear reactions fire up, you're not going to get very far. Certainly it's a very different universe. There's a very good discussion of it in this paper by Craig Hogan. What he says is that, it's a very robust place to place an anthropic bound, because there are a number of problems here. If we could still have elements like carbon and oxygen, because the proton would still be stable if it's inside a nucleus. So you can still have some of your periodic table if you like. The problem is that you're going to have a lot of trouble with galaxy formation, star formation. There are additional forms of radioactivity, and in particular, he says that DNA is going to have a hard time being stable because of the nuclear radioactivity. When you have radioactivity in a nucleus, what's happening is that it's ejecting a certain particle and changing. So in particular, if the carbon in a DNA sequence undergoes a radioactive decay and becomes something else, that's a huge problem, right? It's got certain chemical properties. They're not interchangeable. Things are a bit clearer. So that's sort of where we've hit on this side. Things are a bit clearer out to the right. Remember when we went this way, the strength of the strong force got stronger. So if you go the other way, it's going to get weaker. The first thing that's going to happen is that the deuterium is going to become unstable. This step won't work because that will be unstable. Okay? If you put these two together and make deuterium, it will fall apart before any of these other steps happen. It's a bit like if you were making a cake and you cracked an egg into the flour and then stirred it in and then went to get the milk, and by the time you came back, it had separated back into the egg and the flour, right? If you're starting your recipe and it keeps going back where you started from before you can do anything else, then you're in big trouble. So in that sort of universe, stars will be more difficult to fire up, and in particular, most of them just won't. They'll be stabilized by degeneracy pressure before they become stabilized by thermal pressure sourced by the nuclear reactions. Even clearer is if you increase the Higgs parameter by a factor of 5, even inside the nucleus, the neutron is unstable. And this is that catastrophic, the chess and the checkmate example. All nuclei are unstable, okay? This would be great for chemistry because the periodic table would look like this, okay? It would be so easy, okay? There would be no one around to do chemistry, but chemistry would be fantastically simple, okay? So that has happened, sorry. That is this bound here. So there are no stable nuclei. Further out that way, yeah, there is this blue region here, but it's not likely that that's a life-permitting region as well. What's happening here is this, you might remember, is the proton, 2 ups and a down. As you hit this region here, this particle, which is called a delta plus plus, which is an up and up and an up, 3 ups, right? That one becomes lighter than this one. So remember I said with composite particles, it's the lightest ones that are stable. So then this one becomes stable. However, you still can't make nuclei, and what you've swapped is you've swapped a proton which can make hydrogen, which can make one compound, for a nucleus which is basically the same as helium, which can make no compounds. So you've really not gone too far well there. Okay, so all of this is out of bounds. Okay, nothing interesting is going to form out there. As you go this way, things get a bit weird. So let me explain what's going on here. If you're out in this region, the problem is you've made the electron very light. Now, what that means is it's easy to move around, so that chemical energies become very low. Now, you can only make chemical compounds in the universe so long as the temperature is low enough that compounds don't get blown apart. So, compounds only form when the cosmic microwave background, all the photons that fill the universe, has a very low temperature. So if you're out in this region, you have to wait so long for that to happen that actually the proton is probably unstable on those lifetimes. By the time the universe is cool enough that you could make you could do some chemistry, you've got no protons. Okay, so that's no good. Even closer in this sort of region here, we're in a bit of trouble. Electron mass is so small that cooling for stars is very inefficient. And in particular, so a typical number that they give here is that a star will take about 10 to the 17 years to form, but then the star will burn out very quickly, and so it'll burn for about a year. So it'll take you, what is that, 100 trillion years to make a star, and then that will last for a year. So we can, I think this region is also pretty solidly ruled out. Okay, but this is the kind of thing that we want. We want these really catastrophic changes. You know, we don't want to be wondering, you know, will life form in this universe? I mean, no, nothing will form in that universe. Nothing interesting. There's one, you know, the periodic table is one element that will do nothing. We can look at the same points in a few different ways. I'll show you this plot just because it's interesting. So these people did. This is quite a nice paper, again, Physical Review D, 2007, so it's a bit more updated. But I quite like this plot. This is, what they're doing now is not the Higgs mass, they're just changing the masses of the particles themselves. So pick the mass of the down quark and pick the mass of the up quark. So that's these two axes. These are logarithmic axes as well. In this case, annoyingly, it's not log base 10, it's log base e. So every time you move 1 is a factor of e. Do you remember e from high school? Yeah, 2.78 something. Anyway, this is the allowed range. The upper limit here is the Planck mass. Above that, we would need some sort of quantum gravity to know what's going on. So what happens up here, who knows? You know, there be dragons. The lower mass is related to something called dynamical breaking by chiral symmetry in quantum chromodynamics. That would take about an hour for me to explain, and I'd probably get it wrong. But there is a lower limit there. Ignore these lines. The important point is this box. That's our universe there. This box then we blow up to this one. All of these different lines are different criteria that a universe plausibly has to pass in order for it to have life. So, for example, if you're above this blue line, then the only stable particle is that delta plus plus particle. If you're below that blue line, sorry, out to this side of that blue line, the only stable particle is a particle called delta minus. Again, you just get hydrogen, so that's kind of useless. I won't go through these lines in detail. It's the same sort of physics I had for the other case, but just sort of arranged differently. The point is, the only place where you satisfy all of these is in that little green spot there, which is, if you zoom it back to there, is actually quite impressive, I think. Remember also, this is a logarithmic scale. If you did this on a linear scale, it would be even smaller. So the point I want you to get from this plot is that there are a number of criteria which all intersect, and you've got to get all of them right. There's no point, being on this side, of this problem if you then run into other problems elsewhere. There's no point, if it's okay, you don't get the delta plus plus particle, but you still get, your stars won't fire up or something. Okay. Let me skip through another couple quite quickly. These guys put just a more definite constraint on this. Is the Higgs parameter again. This is just a range where V is what the range we're considering, and V naught is what it is in our universe. I should make this point clear. I'm not going to ask what the probability is that we would have a life-permitting universe. If you want to do that, you need more assumptions. You need to know how to calculate probabilities in this parameter space. Or I'll just show you what the life-permitting region is. And then if you want to go calculate probabilities, I'm sure Robin will be talking about that more tomorrow. All right, let me skip ahead a bit. Here's another plot. This is a nice little article by Tegmark from 1998 with a very interesting title, Is the Theory of Everything Merely the Ultimate Ensemble Theory? That article deserves a talk on its own. Okay. This is the fine structure constant going from naught to infinity. He's rescaled the axes so that he can fit all of that range on. It's quite a clever trick, actually. There's an inverse tangent involved. And this is the strong coupling constant, alpha S, if you remember those from. So here's our universe here. I can make the strong force stronger, or I can make electromagnetism stronger or weaker, or some combination of the two. So the obvious ones are, if you're in this yellow region, then carbon is kaput. It won't be stable, so that one's gone. Here you have no non-relativistic atoms. What that means is if the electron in its orbit has to move too fast, it's moving so fast that it's got enough energy to make it's got enough energy to make its own antiparticle, basically. You've got so much energy there that the electron it'll form an electron-positron pair and just annihilate. That's the physics of that is a little bit complicated, but that is another disaster. Just atoms aren't stable. The electrons won't stay there. This is the diproton disaster. Again, disaster, maybe not really. If you want to get Big Bang nucleosynthesis right, if you want to have leftover hydrogen, actually, from those other papers, that's this level here, which I've shown. This line means something that I should look up. Below that line, deuterium is unstable, so the first step in stars doesn't work. And so it's unlikely you would get stars to form. So you see, again, all these regions, you have to get yourself in the right spot with respect to all of them. There's no point being, okay, carbon is unstable, but all my atoms fall apart. Okay. I'm going to spend a little bit of time now on. This is a very famous case. This is called the triple alpha resonance, and it's actually one of the first fine-tuning cases. The story goes that there was a very famous astrophysicist, Fred Hoyle, who was at Cambridge, was working out the physics of nuclear reactions in stars. And what he worked out was, he was working out the rate at which stars make carbon. And he worked out that his calculations simply weren't working. They weren't producing the right amount of carbon. So he thought, okay, there must be a missing ingredient. And the missing ingredient was that there is a resonance level in carbon. What that means is there's a sweet spot, if you like, so that there is a form of carbon, an excited state of carbon, which forms a sweet spot so that this reaction goes faster. Let me try to explain that a little bit more. Here is, if you just have a carbon nucleus and just in its ground state, the lowest energy state it can have, that is this sort of energy level. Okay? there is also an excited state of carbon. So think about all those neutrons and protons together, and if they all sort of jumble around in a certain way, there's an excited state there where they're all sort of moving a bit faster than usual. But because this is a quantum system, there's not much in between. What he showed was that if this state is close to these two states, so what do we have here is I'm trying to take 3 helium nuclei, and then I'll make beryllium out of 2 of them, and then throw in the other helium, and I'll make carbon. If these 3 states are all close to each other, that reaction will go faster, and will go fast enough that stars will actually make carbon. This is not to scale. Let me show it to scale. It's chopped off the top. Sorry, won't be a minute. Yeah. You see the red? Okay. That should be slightly higher, but for the purposes of, it's roughly about right. So, if you have to jump from this state to this state, there's the ground state again, that reaction is slow. But if you can jump from this state, you put these two together, and then you make that one, and then that jumps to the ground state, that's faster. Now, the paper I gave was by Livio et al. What they showed was if you move that resonance by about twice the thickness of that line, you drastically change, well, you quite significantly change how much carbon is made in the universe. The issue here is if you move too far away from there, the stars will make either carbon or oxygen, but not both. You make one at the expense of the other. If you take a carbon C12 and then you combine that with another helium nucleus, you make oxygen. Now that's useful. You want some oxygen, but you want both, right? I mean, you're carbon and you're breathing oxygen. We need a bit of both in our universe. Now, there's a question of should I think of that as being scaled relative to these guys, so that actually it's not that much of a fine tuning, or relative to this scale, in which case it does look pretty particular that on this scale you manage to hit exactly that spot. Thankfully, this has actually been answered by another paper in 2000, although there are a few caveats coming up. What they showed was if you change the strength of the nucleon-nucleon interaction, so that's basically the strong force, okay? Here's how this plot, just focus on this plot. I'll take you through it slowly. There is our universe. Look at this top axis here. So if I go to there, minus 0.4, never mind. That means I've made the strong force weaker by 0.4%. Okay? What that means is I made, which one's which? Uh-oh. Okay, I've forgotten. One of these is carbon, one of them is oxygen. I've made about the same amount of, say, oxygen, but I've made significantly less carbon. So there's our universe there. If you go out the other way, so 0.4% stronger, again, I've made one of them, but at the expense of the other. So to get the balance right, there's a very narrow window in the strong force where I actually get these right. Now, this is another slightly cautionary tale, because the same guys then published a paper 4 years later saying, actually, it's not quite as clear-cut as this. Look at these black triangles, okay? So as I make as I change where the resonance is, the black triangles, which were the old points, sort of dip down pretty quickly. They're new calculations which just did it in a bit more detail, a bit more carefully, don't quite dip as fast. So there is a little bit of caution on this one. Also, there was another paper which did the same sorts of things. Actually, I won't go through that one. Okay. That's that same plot again. This one, this is what I'm after. Okay. This looks similar, but it's actually different. This axis is the same. This is the electromagnetic This is the fine structure constant. This is now the ratio of the mass of the electron to the mass of the proton. So once again, we see the no relativistic atoms bit. If you are below in this yellow region, remember the window for stars? If you were too small, then degeneracy pressure would hold you up and you wouldn't kick off nuclear reactions. If you were too big, radiation pressure would make you unstable. Okay? If you choose your universe, so here's us here, but if you were to choose the value of these coupling constants, so you were in this region, that window would close. There would be no way of satisfying them both. If you were big enough to fire up nuclear reactions, you'd be too big and unstable. So there are, in this case, there simply are no stable stars. So once again, we see the no ordered structures bit. If beta is too large, then it becomes much easier to melt solids. They're positioned in a lattice. So if you remember our picture of solids as just sort of atoms lined up in grids. They jostle around in those grids a bit. The bigger you make the electron mass, say, the more they jostle around. And so if you wander up into this section, basically solids aren't stable anymore. You can't, you literally cannot make solids. All you can make is liquids and gases. That's not particularly useful if you want to make something nice and stable like DNA, which is, after all, solid. Okay? Now, is chemistry itself fine-tuned? Now, the answer to this is actually not as much as you'd think. These are, if you remember, all the levels that the electron can have in an atom. Now, it turns out that all of these electrons, they don't depend, you don't have to fine-tune these one by one. Actually, the fundamental constants of nature just change the scale. It's the equation of quantum mechanics, the Schrodinger equation, for those who know about these things, that determines where all these levels are. So all that complexity is actually in the equation and not in the fundamental constants. Moving on, let me get to something a bit more interesting. Okay. This is a collection of the different mass scales I had. You remember, if you make a rock a certain size, it becomes so big it becomes a planet. If you make a planet too big, it becomes a brown dwarf because degeneracy pressure sets in. Make a brown dwarf too big, nuclear reactions fire up and it becomes a star. And if you make a star too big, it falls apart. It's important that this is smaller than this, which is smaller than this, which is smaller than this. Okay, so you need to get these all sort of in the right order. If that was, say, the smallest one, then the biggest thing you could make would be itself unstable, and so none of them would exist. Okay. You also need to make sure that your lifetime of your star is long, which, as I mentioned before, is because gravity is so weak. Okay. Let's move on to cosmology. I've given a brief overview there of some of the things you need to do to make sure that those equilibria are still there. Remember, I went through all those the equilibria, the things you can make. So if you've made those, then the question arises, what will the universe actually make? So one of the biggest problems here, I think the thorniest problems here, there's two there called the flatness problem and the cosmological constant problem. These have to do with inflation. I will talk about those in the next lecture when we get onto the multiverse. So more of that coming up soon. You'll remember I talked about there's a stage in the universe where for every billion antiprotons there's 1 billion and 1 protons. Now that might sound like it's a good case for fine-tuning, right? Because if you got that a little bit differently, well, certainly if they were equal, then there'd just be no matter in the universe. And there are other problems there. I don't think this is actually a clear case of fine-tuning, and it's an interesting case of why something isn't a case of fine-tuning. Simply because we don't have a good theory of why that is true. We don't know how to predict that number, for every 1 billion, one in a billion more. We don't. There's no formula we have where we can say, okay, now let's change the strength of the strong force and see what happens in the universe. We just don't have the physics there. So to make a fine-tuning argument in that case, I think would just be just a punt to ignorance, really. We don't know, and I think that would give sort of fine-tuning a bad name. In these other cases, we have a good theory of, say, stars, and we know what would happen if if the fundamental constants were different. We can make those predictions. So for the case with the protons and the antiprotons, we can't do that. We just don't have the theory. So it would just be ignorance, and we don't know. Let's discuss quite an interesting case. Entropy. Entropy is a very subtle concept. If you took all the gas in this room and you put it all over, say, in this region here, okay? Overwhelmingly, the most likely thing that would happen is that it would all spread out back into the room. It would fill the room in certain cases, in more or less uniformly. The reason is that if you have a particle which is on the edge of this ball, it's still moving around. So if it's moving away, there's nothing to bounce it back in, and if it's moving in, it'll probably bounce away. So this ball of gas here is going to just disperse back out into the room. Okay? What we say that is because entropy increases, so that it is not absolutely certain that that ball of gas will disperse out into the room. It's just overwhelmingly more likely. Okay? So that the ball of gas is itself a low entropy state, and with all that gas dispersed through the room, that is a high entropy state. Now, when you put gravity into the equation, things get different, because gravity tends to make things actually clump together. These guys are just bouncing off each other, whereas these guys are actually attracting each other. So with gravity, as entropy increases, it actually clumps together. Now, what this means is actually, when you look at the very early universe, if this is a low entropy state when gravity is involved, and this is a high entropy state, the thing is, the early universe looks an awful lot like this. So the early universe is shockingly uniform. The biggest deviation away from uniformity is about 1 part in 10 to the 5. So if you took the average density, say in this room, and then you go take the density in little bits of the room, they wouldn't all be exactly the same, but they'd be nearly exactly the same. So the same sort of thing happens in the early universe. The biggest departure away from the average is 1 part in 10 to the 5. Okay, so it's just shockingly even, especially in terms of gravity. Now, this argument is taken up by Penrose in his book. He's a professor at Oxford. He's a well-known physicist. The problem is, entropy when gravity involved is a bit sticky. We can't just take, when we're talking gravity, we're talking about general relativity. So we're talking about a space-time, a curved space-time. We can't just take a curved space-time and calculate its entropy. We don't know how to do that yet. So what Penrose does is takes the argument very slowly. So he says, okay, look at the universe 1 second old, and it is just ridiculously uniform, to 1 part in 10 to the 5. Okay, now let's run the tape of the universe forwards. What we see is, you remember the galaxy formation simulation. The rich get richer, things start clumping together, entropy starts increasing. Now suppose that the expansion of the universe were to stop and stall, and the universe started collapsing. Well, in that case, it's plausible that the clumping would continue. There's no reason for them to suddenly all spring apart again. So and now let's keep running it forward. So we keep getting clumpier and clumpier. We make black holes, which are just the ultimate in clumpiness. And just before the end, let's now freeze it 1 second before the end. So on this end of the universe, 1 second old, perfect uniformity, everything very, very even. On this end of the universe, the black holes have merged together. They've made singularities in our, we had such a nice space-time. And now it's just full of singularities and clumps and bumps. So what he says is, okay, if a whole load of entropy increasing processes made sort of this universe into that universe, made the very smooth one into the very clumpy one, then this very smooth one must represent a low entropy state, and a very special state. I mean, that's basically what entropy quantifies. That's what it does. Entropy is about, in all of the ways the system could be, is this a likely one or an unlikely one in a certain very well specified way. So what Penrose's conclusion is that actually our universe started off in an extraordinarily special state. And he has a slightly famous image in his most recent book, The Road to Reality, where he thinks about a phase space, which is just the space of possibilities for how the universe could have started off. And this creator has to find a very, very special spot to start a universe off in such a low entropy state. So yeah, a fanciful description. His calculation is actually pulls out a ridiculously small number. 1 part in 10 to the 10 to the 123, which is an astonishingly small number. Now, I'll have more to say about this because inflation has something to say about this. So there'll be more on that later. But I think actually it doesn't turn back the force of this argument. So I think this is actually quite a good fine-tuning case. So a very robust fine-tuning case that actually the start of our universe is not a generic sort of Big Bang. The whole point of this argument is that a sort of generic, normal, run-of-the-mill Big Bang would produce a universe with black holes and all sorts of, pockmark, lumps and bumps like this one, not the sort of perfectly smooth universe we see. Finally, let's have almost finally, let's have a quick look at galaxy formation. This is a wonderful paper by these guys. We see Tegmark again. Aguirre is well known. Rees is Sir Lord Baron Professor Rees of Ludlow. He's the astronomer royal. So he's at Cambridge, and his reputation preceded him. So it's one of those cases where you actually walk in and he's quite short. You think, wow, that's Martin Rees. Wow. And just to top it off, the fourth author, they let a Nobel Prize winner tag along. Yeah, he won the Nobel Prize in 2004. So this is a super duper paper. We're going to come up against another one of these confusing diagrams, I'm afraid. It more or less explains itself, doesn't it? We can get this, all right? I know I'm in the afternoon session where we've all just had lunch. We're all feeling sleepy. I can see that. We can do this, okay? Make a collapsed object in the universe. So the idea, think about the universe making structure, those simulations that I showed. Once you've made something, it would have a characteristic mass and a characteristic size. With those, you can calculate a characteristic. They use different. These are just different axes. But this is a characteristic temperature that the gas will have, and a characteristic density. So how many protons there are per cubic meter. Now, this shows our universe. So we're not doing fine-tuning yet. This is just a way of showing galaxy formation in our universe. The important points are these two sort of bananas, okay? The green one shows the rate at which those types of, so the rate at which, okay, so I have a particular temperature and a particular gas density. So the green shows the rate at which those ones are made. And the yellow one, sort of at yellow, orange, red, shows the rate at which those ones are destroyed by being eaten up by bigger ones. So you have two collapsed objects, one's very big and one's very small, and if this one sort of gets eaten up by that one and they form one big one together, then that is a destruction. Okay? Now, there's a bit of physics going on here, so let me say what's going on. If you make a halo in this region, the two close encounters, the problem is that your galaxy will be so dense that a planetary system won't last very long before another star wanders through it. Now, that, as you might understand, is pretty disastrous. Okay, if we're on nice circular orbits around the sun, because the sun is the heaviest thing around, if another star wanders past, things could get, we could very easily be sort of thrown into one star or thrown off out into the solar system, out into sort of empty space. So this region here is no good. If you're out here, you've made a black hole, so not much going on in there. Any matter that falls into it just gets crushed into oblivion. If you are underneath this thick black line, which is a very complicated shape for various reasons, if you are underneath there, then the galaxy won't cool. The gas in the halo won't cool. So you won't make a galaxy with stars and planets, you'll just make a big hot ball of gas. So that's no good either. And if you are out in this region, then there are no second generation stars. Remember, when stars get to the end of their life, they blow up in supernova. If you make a galaxy here, a halo here, the first supernova will blow it to smithereens. So remember, we need second generation stars, because the first generation stars, we need second generation stars because planets will form around second generation stars. The first generation make the elements that will make the planets, but we'll only make the planets if there are more stars for the planets to form around. Now, this is just our universe, and in particular that star there is the Milky Way. What happens now is we start changing the laws of nature. Okay? In particular, we're changing the initial conditions. Now, they use a couple of weird symbols here, but it's okay. What's really changing in this diagram when you change the laws of nature is the banana. Okay? This is basically the total amount of matter in the universe. If you start putting more and more matter in, then preferentially the banana goes up, so you make more and more dense galaxies in which planets can't form. Oh, they will form, but sooner or later a star wanders past and that solar system just gets disrupted. This is if you increased this parameter. If you decreased it, you eventually get to a point where you don't make any halos that can cool gas and make galaxies. So that's no good either. This is Q. Q is the level of inhomogeneities. That 1 part in 10 to the 5, that's Q. And you see basically the same effect, slightly off to one side. A reasonably similar, this is the baryon fraction. So what is the fraction of normal matter to dark matter? So if that drops, then cooling gets harder, and you eventually start making halos that simply can't cool. The cosmological constant is a form of energy that makes the expansion of the universe accelerate. What that does is it actually bites off the banana at a certain point. If, how to explain this? Past a certain point in the universe, there is simply a certain time in the universe past which structure formation stops. So all that, the rich getting richer, things going in, just freezes. Everything expands so fast that nothing can fall into anything else because it's all been blown too far away. Okay? If you make the cosmological constant too large, that happens before any structure forms. And so you just get nothing. Okay? Let me summarize these in one nice little plot, which is this one. So this is epsilon, this is how much matter you put into the universe. This is Q, that 1 part in 10 to the 5. And so these are all those problems that we were running into. If you're up here, you just make black holes. If you're down here, or in this region, for different regions, but for different reasons, but the outcome is the same, your galaxies just won't cool. If you're in this green region, you will make galaxies, but they won't be able to fragment and form stars. So that is a quick summary of fine-tuning in that case.
What are the shapes? What's the star?
The star is our universe. Yes, the star is our universe. The triangle and the square are basically, if you fix this parameter and said, okay, how far up can I go, then you would end up here. But if you think, it's kind of hard to explain. I'll get to it more when I get to inflation, I think. Remind me.
Can I raise a comment because it's
Yep.
relevant to my talk tomorrow? One of the problems with these cases, because I don't think they've thought about the issue of fine-tuning in sufficient philosophical depth, is that all you're getting here is a density of observers or whatever light optimality at most from this sort of argument.
Yeah.
Because if you start moving the stuff off, let's say you get a more dense galaxy, more likely collision, well, that's just a likelihood. So more likely than not, the orbits will be disrupted or something will happen. But still, statistically, occasionally, you're going to still get life arising. It's not going to happen. You're not going to get a star coming by and destroying life on the planet. So you'll still get observers or life or whatever your thing you have is. So why should we care about density of observers? Why should that matter in either a multiverse or a theistic scenario?
I think there is a useful distinction to be made between sort of normal observers and freak observers. Not freak observers in the Boltzmann brain sense, which I'll get to, but just observers that have to wait for some really freakishly unlikely thing to happen before they can actually form.
This is probably the case in our universe anyhow. I mean, especially if you take a rare Earth sort of scenario, that it's not going to happen very often. There's a lot of the asteroid killing off the dinosaurs. There's a lot of freak events that had to come into play for life to have occurred at all.
Yeah.
So we're all freak observers in that. We're all freaks in that.
Yeah, it's good to know.
We'll put that on a T-shirt.
In one of your, I think it was one of your articles, you argued that it would still be interesting even if we were somewhere near the peak for life. If in sort of parameter space you had sort of the probability of life forming, say, in a Hubble radius or something, even if that never really dropped exactly perfectly to zero anywhere, it would still be interesting if we were somewhere near the peak of that.
There's a peak in terms of density. What I want to say is a really relevant factor, because I have the interacting agents that can morally connect with each other, morally influence each other, and then can discover the universe and develop technology, which I think the technology drastically increases that. That's the really, that I think is a relevant kind of optimality.
Okay.
And this only is giving you a sort of, even the cooling trouble, I think it's only giving you a density per co-moving volume.
Yeah. Do people get the point here? The point is that these aren't, somewhere in the universe, some freakish planet might be able to avoid close encounters for long enough for life to form. Our universe apparently isn't like that. But is life in this universe impossible, or is it just really, really improbable? And it's probably just really, really improbable. What do we do with that sort of case? I think I might leave that to you.
It's not just really, really improbable in the universe, because in current cosmology, often in inflationary cosmology, universes, typical scenarios, infinite in size, it can be indefinitely large.
Yeah.
There's no upper bound to its size, so you can have any probability to one of life occurring there, even no matter how freak it is in any galaxy.
Yeah.
Because you've got all this space to be working with. So it's really only very unlikely within a certain volumes per galaxy or something like that,
Yeah.
which you're arguing for.
Okay. I'll let you flesh that out tomorrow. Let me finish with a quick case, a kind of an interesting one, which is how many dimensions of space and time there are. So we are here. We have 3 dimensions of space and 1 dimension of time. But we can imagine, certainly we can mathematically describe universes which have more than 1 space dimension. For example, if the universe was had 4 space dimensions, then you could take a right-footed shoe and using only rotation make a left-footed shoe. Okay, so these things are kind of counterintuitive. If you think about your hand is, you can sort of rotate it. It looks like the other type of hand. This is amazing. It's only once you have a top and bottom that there's a difference between the top and bottom. But in 4 dimensions, you can get around that. One of the most interesting cases is, okay, if you are in this region here, say there are 2 spatial dimensions, it seems like complexity is going to have a hard time in that universe. For starters, this is a slightly technical point, but general relativity, if there are only 2 space dimensions, doesn't have a solution in vacuum. What that means is there is no gravity outside of matter. So there's no gravity in empty space. So planetary orbits would be in trouble. Also, you might remember from, who's read Brief History of Time by Stephen Hawking? Okay. Who's really read A Brief History of Time by Stephen Hawking? Okay. You might remember there's a weird diagram in there which looks like a dog cut in half. Do you remember that one? The whole point of that diagram is that we have a digestive tract that goes through our body, but because we have 3 dimensions, we can wrap around that digestive tract. Whereas if you have a 2-dimensional animal and you put a digestive tract through from one end to the other, it cuts the animal in half because there's no way to go around it. So in 2-dimension, lines can't cross without intersection. In 3 dimensions, you can go over the top, but in 2 dimensions, so they're very, complexity becomes a lot more difficult. If you have more spatial dimensions, for example, let's look at gravity. If you take Newton's law of gravity, you express it in a form which is called the Poisson equation, which doesn't obviously contain the sort of dimensionality of space. And then you change that, you use that to predict what gravity would be like in higher dimensions. Let me show you this. Suppose that you're in a 3-dimensional universe, this is our universe, and you have a nice circular orbit. In 4 dimensions, that is still true. You can still have a perfectly circular orbit. However, if you miss it just a bit, suppose you're up here, there's the sun in the middle, and I have my planet outside, and I throw my planet into an orbit. If I get it perfectly right, I get this red one, which is the perfect circular orbit. If I miss it by, I think, remember, 1%, it's still roughly circular. So your mistake doesn't get penalized too badly. You just sort of miss it a bit at this end, but then it sort of corrects itself at the other end. In 4 dimensions, this actually doesn't work. You get punished quite badly. So here is our perfectly circular orbit. You miss it by 1% too slowly, and this black line curve, so you just sort of spiral into the star. No good. And if you miss it 1% too much, then you get the blue one and you head out, away from the star. So if this is your source of power, you need to stay at a pretty constant radius. So in a 4-dimensional universe, that's not going to happen. This result also holds in general relativity. So it's not those calculations that I showed were in Newtonian gravity, but it's a perfectly general result. It also applies to atoms. In 4 dimensions, atoms, the problem is that there is no ground state. Remember, I showed all those levels in the atoms. There was a bottom one. It was the bottom one that's important. You couldn't go any lower. In 4 dimensions, there is no ground state. You can just drop right into the nucleus. The other cases where you have more than 1 dimension of time, are obviously a bit weird. There's no problem calculating what things would be like in physics, but actually what experiencing a world with 2 time dimensions would be like, we don't really have any idea. It's possible that single observers would just observe their own, like if I go this way, I'm sort of observing my own dimension of space over here. Each observer would have their sort of own path through time. I really don't. Anyway, the point of this section here is that in such a universe, you can't, the universe becomes unpredictable. For example, you remember that the lightest, with composite particles, it was the lightest ones that are stable, but now that doesn't put any sort of barrier anymore. If time were 2 or more dimensional, there would be nothing for a proton to decay into a neutron or positron into a neutrino. The stability that we had there in the basic constituents of matter would be lost because energy conservation would be a very different kind of thing. Now, sorry, just to explain this bit again. In those sorts of universes, you can't predict the behavior of your surroundings using only local finite accuracy data. So if I can predict how this thing is going to act using, I don't have to worry about what's happening on Pluto to know where this is going to land if I throw it. And I don't need to know exactly accurately how hard I've thrown it. If I get it roughly right, that'll do. Okay. Whereas if in this sort of region, if you have started more than one time dimension, that falls apart. The universe simply becomes unpredictable, which is bad if you want, say, a brain which can record information. If your brain records information, but then that information chaotically fluctuates, you're in a bit of trouble. You just can't process information. Finally, a tachyon is a particle that can move faster than the speed of light. So if you're in this region, there are only tachyons, there are not normal particles. In particular, photons are unstable, so the light particles will decay. So that's not a particularly useful kind of universe. I've run out of time, haven't I? But I've basically reached the end of the fine-tuning bit, so we'll be on to the multiverse, and things will get weird in the afternoon. So stay tuned.